So we've learned a lot of things about different dynamic modes of that typical aircraft experience. And we're going to take a minute here and summarize what we've learned about these dynamic modes. So we're going to look at, we're going to list out the modes here and talk about the components as well as the damping and the period, and finally 99% damping or doubling time, as the case may be. Okay, so we learned about two different fundamental types of modes. We learned about longitudinal modes and lateral. So let's start off with longitudinal. And in the longitudinal world, we found that we had two what are called rigid body displacement modes. So these are rigid body displacement modes. And those modes basically came from two components in that set of equations that we said that the solution was independent of. And so in the longitudinal world, we learned that that was independent of our x location and our altitude, since we weren't accounting for changes in density. And so those are anyway, we're not going to go into that anymore. We just found that there were two modes that came out as zeros. So the eigenvalues that came out of that were perfectly zero. But then we got two sets of complex eigenvalues as well. And one of those comes from the short period mode. And by looking at the eigenvalues, we were able to see that is largely composed of changes in angle of attack and altitude, which we call z sub f. And so that's our height above ground, that z sub f. That's the z in the Earth fixed coordinate system, which is altitude. This is a heavily damped mode. So heavily damped and with a period on the order of a few seconds. So we're going to say like 1 to 3 seconds. And then 99% damping on the order of about 1 to 5 seconds. So in most aircraft, we're only going to experience one oscillation here. It feels just like a bump, basically. This is what you feel when we hit turbulence. When we hit abrupt turbulence, the aircraft just feels like it hit a bump. And that's that short period mode that then damps out. It's heavily damped, so it damps out really rapidly. Within 1 to 5 seconds, it's 99% completely damped out. The other two eigenvalues that we got out were a complex pair that form what we call the phugoid, or the long period. And these had components, by looking at the eigenvectors, we could see that the components here were mainly changes in velocity as well as altitude again. So z sub f. This is a lightly damped mode, usually, compared to the short period. And so it can persist for quite a while. It's an oscillatory mode with a period on the order of, it usually can be greater for manned aircraft. It can be greater than 30 seconds. And then the 99% damping time of several minutes. So we're going to say greater than minutes. Okay, so it can go on for a few minutes. So we're going to naturally, if the pilot doesn't do anything to suppress this mode, this will persist for some time. It can be for several minutes, and we'll experience several oscillations of the phugoid. Okay, so these were the longitudinal modes. Then we also looked at lateral modes. And again, we got out two rigid body displacement modes. And that's because there were two parameters in there that don't matter, such as heading, for example. It doesn't matter what direction the aircraft is headed. It will have the same dynamics. So that's one of the sources of one of those rigid body modes. So anyway, again, those come out as zeros, as eigenvalues, and then we got 4 non-zero eigenvalues. And two of these are usually real. Okay, so those the real ones are for the roll mode, and so the roll mode for one of the real ones, it's a roll mode. That's a change in our rolling rate, so it's related to P and phi. So that's our how quickly we approach a steady rolling rate, and we usually sense that through a change in bank angle. This is a highly damped or heavily damped mode, and it's not periodic, so it's not oscillatory, and it is usually 99% damped out in less than a second. Okay, so less than 1 second. Okay, so it's not periodic. And then the second, because the roll mode is usually real, that means that we're going to get out another real number out of those eigenvalues, and that other real number is related to the spiral mode. And the spiral mode is mainly a slow change in our heading. It's lightly damped, and lightly damped, or can even be undamped. So this can even be divergent, and that's okay as long as it's slowly divergent. So the 99% damping time, again, this is not periodic, so we have nothing there. It's not oscillatory. The 99% damping time is usually on the order of several minutes. Or if it's divergent, then we'd be looking at the doubling time, and we want the doubling time to be on the order of the longer is better for the doubling time. The shorter that doubling time is, the more dangerous that mode can become. So anyway, usually this mode is not of a whole lot of concern. Usually these are just lightly damped or slightly undamped, and it's not really much of a concern for the pilot. Okay, so both of these are real. We get real numbers out here, where the others have been imaginary. At least these two here are imaginary, and then the other two that we get out of the lateral side are a complex pair. They're also imaginary, and those are for the Dutch roll mode. Okay, so these are complex numbers that come out, and these components, the Dutch roll mode is a combination of roll, yaw, and side slip, and it's this out of phase combination of all three of these things. It feels like you're fishtailing. It is oscillatory. Usually it's lightly damped. And now it can be lightly damped or heavily damped. There's a range of damping here. So I'm actually going to say lightly to heavily, depending on the yaw damping. So of course, if you have a yaw damper on board, then that will be heavily damped. That's taking care of it. But if you don't have a yaw damper on board, just the natural physics of the aircraft are probably going to be closer to the lightly damped. This can have a period, because it's oscillatory. It will have a period, and that's usually between about 2 and 10 seconds. And so again, that can be dangerous because this 2 is on the order of pilot response time, and so then that's when this mode can get dangerous. And then the 99% damping time, if it's lightly damped, this can sometimes go on for greater than, we're going to say, about 10 seconds. So we'll usually experience a few cycles of that before it completely damps out. Okay, so these are the lateral modes here. And again, I've pointed out the real numbers here. This is imaginary or complex pair. These are each a complex pair here, and then the rigid body displacement modes are just equal to 0. So that's how you recognize those coming out of an eigensolver. Now I want to just mention two more things here. One of the things is we've assumed in our analysis here that the aircraft is a rigid body. Okay, so I'm just gonna come down here and say just a couple of assumptions to keep in mind in the analysis that we've performed here. So the first is that it's a rigid body. And so we've neglected any flexibility of the aircraft. It turns out the aircraft are actually highly flexible, most of them. That's because they're trying to keep weight down on the aircraft, and so you tend to get the structure as light as possible. And light structures are more challenging to keep stiff, and so of course they have certain designs and things to stiffen up that structure, but still most aircraft are fairly flexible. And so there's a whole world of study of the flexibility of aircraft called aeroelasticity. Aeroelasticity. And there are complete books and courses on that topic alone, and that's basically studying the coupling between the aerodynamics and the structures of the aircraft. These two things couple because as you load up the aircraft, of course, your wing bends under that loading. For example, when you're sitting on the runway, the wing, if the landing gear is in the fuselage, then when you're sitting on the runway, the wing is hanging off of the fuselage. But once you get up in the air, they kind of reverse rules. It's more like the fuselage is hanging from the wings because the wings are providing the bulk of the lift to keep it up, and then you have the weight of the fuselage where there's a concentration of weight there in the center that's basically hanging from the wings. And so if you notice, next time you fly, you're looking out the window, you can kind of see where the wingtip is while you're sitting on the runway, and then once you lift off the ground, you'll see that wingtip move upward. You know, as you produce lift on the wing, that wing will move upward, and these wings are actually designed to be somewhat flexible. Of course, they usually try to make them as stiff as possible, but because of the light materials that they're made of, even the carbon composites and things, you're still going to see some flexibility there. And so it's pretty amazing how far these wings can deflect before they fail, before they snap under load. So anyway, the bottom line here is that we've assumed that all of our aerodynamics and things are not at all affected by the aircraft, or in other words, that this is a rigid body aircraft, that our aerodynamics are not affected by the structure. But in general, that's not true. The aircraft is going to change shape slightly throughout the flight based off of the weight that it's carrying and fuel burn and where that weight is being carried and things like that. And that's this world of aeroelasticity. Now, there's another thing in aeroelasticity that we need to be aware of, and that is the frequencies of that elastic dynamic system that is the structure of the aircraft. So if you think about, and maybe if you think back in your statics and dynamics courses, for just a simple beam, for example, that a simple cantilevered beam, if you deflect it down and then let go, it's going to vibrate at a certain frequency. And so there are certain modes within that beam, and there's a bending mode, there's a torsion mode, so it will twist at a different frequency than it bends, and then you have different frequencies. If you double that frequency or whatnot, I forget all the intricacies of how that works, but anyway, there are certain frequencies that structure is susceptible to, and so what you want to do in the design of your aircraft is make sure that these modes, these dynamic modes that we've talked about here, do not happen at any of the frequencies of your structure. Now, luckily, and the reason you wouldn't want those to overlap in frequency is because then they can take energy from each other and basically add to each other. So they can hit harmonics and add and begin to resonate and anyway, pretty soon your structure, this is actually what happens with flutter, basically, is that your structure begins to resonate because of the aeroelasticity until it can resonate and increase in amplitude until the structure falls apart. So you certainly don't want any of these modes, these frequencies that you're going to experience in flight due to disturbances in the air or control input or whatever. You certainly don't want any of these to excite modes in your structure. And so luckily, these frequencies that we see here are usually really low frequency compared to structural frequencies. And so usually we don't have an issue with that coupling, between these different modes coupling with structural modes. But it's something to be aware of. You certainly want to know what these are, what the frequencies are of your structure, as well as the natural dynamics of the aircraft or the rigid body dynamics, and just make sure that those don't couple. Okay, so that's one of the things that we need to be aware of, that we've assumed rigid body. And then the second is that we've looked at just small deviations in our flight path, so to speak. So we looked at an equilibrium flight condition. So this aircraft was trimmed, in steady climbing flight or something. And then basically all of this dynamic analysis we studied as small deviations to that. Small deviations in angle of attack, in side slip angle, and anyway, just all of the angles and the rates and things we assumed were rather small. Okay. And it turns out that that's a pretty good assumption for most aircraft. Now, some fighter aircraft may get into modes that are outside of this. They can be highly nonlinear modes, or at really high angles of attack, or just have just deviate, from these small perturbances that we've been talking about here. And so this analysis, you just need to keep that in mind, that this analysis really just pertains to aircraft that are going to experience these small deviations in the aerodynamic properties and angles and things. And it turns out that it's pretty accurate for most of the aircraft that you would ever care to fly on. But that it's, if you're going to work with a very maneuverable aircraft, a stunt aircraft, or a fighter aircraft type, then you would obviously need to do another layer of analysis here that can capture larger deviations. Okay, so these are a couple assumptions just to keep in mind. And again, this has just been a summary of the dynamic modes, going over both the longitudinal and lateral modes. And hopefully at this point, you could get information out of your eigensolver and pick through the eigenvectors and the eigenvalues, and be able to pull out and figure out which modes are which, and perform a complete analysis and learn a whole lot about any particular aircraft that you're designing.